welcome to session 3 on nanomaterials and the properties. So in last few sessions, in first session we have discussed about more or less about the introduction and why do we need nanomaterials and why do we need to study about the nanomaterials. And then in second session we discussed, like, apart from introduction, we have discussed what are the various types of nanomaterials and how do you describe them. So yeah, how do you characterize them based on their dimensions, right? So that thing we have discussed, and also bits and pieces of density of states, dys, right? So we have discussed the density of states in all the three dimensions, and I guess I have derived for 3 dimensions, and also for 1 and 2 dimensions it's quite easy, and I did also introduce the formula itself. So all you have to do was just do some mathematical jugglery, just shift the terms from left hand side to right hand side, and then substitute the k as energy. That's all. So that's all you have to do. Okay, now moving on to section 3. So there is this thing, right? Sir also have discussed the nanoparticles have more energy when compared to the bulk particles, and you people have also have listened, like for if you have a nanoparticle, for example, let's do a demonstration first. Yeah. But first I have a nanoparticle, right? And then also I have a big particle. So let's give these dimensions as 90 nanometers, which is 100 nanometers, right? And this guy is 1 micron. So it is well above 100 nanometers, right? So 1 nanometer will be equals to 10 to the power of minus 9 meters, and 1 micrometer will be equals to 10 to the power of minus 6 meters. So if you equate it, then 1 micrometer will be equals to 10 to the power of 3 times of 1 nanometer, right? I hope I'm not wrong. Yeah, it is. So it is more or less 10 to the power of 3 nanometer. Now because of this convention, so let's say this has, so for example, if I draw the energy plot for a nanometer range, so they have high values, right? When you compare it to this guy, which is the larger one. So this nanoparticle has more energy, right? So the more energy is coming from few different things. The first one is the dangling bonds. Yeah, I have explained this, what exactly are dangling bonds. Dangling bonds are nothing but the unsatisfied bonds on the surface. So whenever you have, so for example, this is my infinitely large body, right? Now what I'm trying to do is I'm trying to cut it in half. And if I try to cut it in half, so there is a new surface formation here, right? And the same goes for other part. Now what exactly is happening there? So what I've tried to do was I tried to break those bonds, which were perfectly bonded inside the material, right? So that's what I'm trying to do. I'm trying to break the surface. So in that process, I have created like dangling bonds, unsatisfied bonds. So for example, last time I took the example of graphene, right? So graphene is more like a hexagonal ring type structure. I made a mistake. It shouldn't be like that. It should not be like this. Yeah, in graphene, like I have said before, you have like 6 membered rings, right? And there is So each carbon atom, at each point you will have a carbon atom, right? Now each carbon atom is more or less bonded to, yeah, it should be like this, yeah. There shouldn't be any, one carbon should satisfy 3 bonds, right? If I draw a graph, if I draw a 6-membered ring here, it will satisfy 4 bonds, so which is not appreciable, right? For one carbon atom you are getting 4 bonds, another carbon there is a 3 bonds, so that structure is not appreciable. So that's why the structure failed when I tried to draw it like this. So it should more or less look like this. So everywhere when I draw a graphing sheet, then my carbon atoms should satisfy a 3 bond relation. Then only this diagram will continue, or this structure will continue. If not, it won't. So here you can see each carbon is now like forming 3-membered ring, not 3-membered ring, 3 atoms, right? So 3 atomic bonds. Now there is 1 atomic bond missing. So because the electrons are found in p orbitals for carbon atom, right? So because carbon belongs to p orbital group, so there is p orbital that is vacant, not vacant. We have, there is no, it doesn't undergo any hybridization, just like it happens in other carbon families like CH4 and methane, ethane, and many other things. Now, and because of this, you have one electron which is freely moving in the orbital, right? Which is not participating in any type of form. So that's how you create a new surface. That means there is one electron that is being not being bonded to other atoms, so which is freely moving, right? Now, yeah. So whenever I try to break a surface, I form a new surface. Whenever I try to break a material, I form a new surface. So one electron is there, so there is no bond formation. So one bond is remaining, and also it depends on. So this is for a simple geometry. Now let's come to crystal structure. You will know when I try to cut the surface, it's just not the one bond. There will be a lot of bonds that are being broken from one atom. You will know that meanwhile. So yeah. Now, how do you say that nanoparticle has higher energy when compared to the bulk particle? Right. So that was the question. Now, as I have again explained in like session 1, but it was I have explained very hurry way because there wasn't enough time to explain that. So I will explain it here again. Why nanoparticle has more energy when compared to bulk particle? Even though nanoparticle has less surface when you compare it with the bulk one. Right, the bulk one surface area is very large when compared to the nanoparticle. So you can see yourself, right? So nanoparticle has a radius r1. Let's say, so surface area will be 4 pi r square. 4 pi, what is my r1? R1 is 90 nanometers. So 90 into 10 to the power of minus 9 square. So this is my surface area of nanoparticle, NP. Now what about the micron particle? So it will be 4 pi. How much was that? I guess it is 1 micrometer, right? So 10 to the power of minus 6. So you can clearly see that the surface area for microparticle is larger when compared to nanoparticle. Right. So higher energy, who is in higher energy then? It should be, I mean, mathematically it should be this guy. Right, when you see it from macroscopical view. But we still say that nanoparticle has higher energy when compared to the bulk particle. Right, when you are talking about the inside atoms, they are all satisfied bonds. So inside the atom is perfectly bonded with all 4 atoms. Right, for example, if I take diamond, or if I take any other element, so it is perfectly bonded with all other atoms. So it is in lower state. So there is no breaking of bond when we are talking about bulk particle, I mean the bulk atoms, because they are perfectly bonded, there is no breakage of bond. And the same goes for microparticle. So how do we say that nanoparticle has higher energy when compared to the this microparticle? So that comes from the energy of states, right? For example, let's take energy of any particle. I hope everyone here knows basic thermodynamics, right? So Gibbs free energy. So any reaction is possible when the free energy is in negative, right? When free energy gives you excess energy gives negative, then only any reaction is possible. And also when something is at equilibrium, right? That means the delta G is zero. When something is in equilibrium, right? The delta G net will be zero. That means the energy is at minimum state. So let's say this is a graph, and E1 will be this guy. This is the hump, and this is E2. So this is my activation energy. This is the amount of energy I need to give for certain reaction to happen. That is called as activation energy. So magnesium ribbon cannot burn itself, right? That needs some activation energy so that it can burn. So magnesium cannot burn itself. There is a need for activation energy. So that's how you take a matchstick and then put a fire into it and it will burn. So that's how you use the activation energy. Yeah. So E1 is at higher state, E2 is at lower state. That means this is the minimum when compared to E1 and E2. So system will be at equilibrium. So even if you supply some activation energy, it will not go back to E1. Right? So if I burn magnesium, it will become magnesium oxide. Even if you supply energy, it will not go to magnesium until and unless you supply tremendous amount of energy where this plus this make sure that this guy will come to here. So that's how you break the bonds between magnesium and oxygen, which is quite hard when you normally do. Physically, when you try to just heat the magnesium oxide such that the bond will break. No, magnesium oxide dissociation temperature is very high because you need to supply this much amount of energy. So that's how the equilibrium comes here. So lower the energy, the better the equilibrium it is at, right? So the stable state, you can call it as a stable one. Now, the first point is to understand if any material or any particle is at lower energy state, like it is at equilibrium, then that must be at E minimum. It should be at minimum energy level. Okay, then let's first take nanoparticle. Now nanoparticle has, and because nanoparticle is very small, so bulk atoms number is also small, right? So let's say our nanoparticle is so small, like for example, let's not even consider 90 nanometers, let's consider like 20 to 40 nanometers. So nanoparticle of 20 to 40 nanometers. Let's say it contains 50 surface atoms. It's just for explanation purpose, not anything else. And let's say 120 bulk atoms. This is for explanation. There is no theoretical explanation why 20 and 40 nanometers has only 50 and 120. It is just for an example. Okay. Now let's talk about bulk one. Bulk one has, which is of 1 micrometer, right? 1 micron. So bulk one has more or less, let's say because its surface is very large. So its surface is very large. So it is like 1000 times of nanoparticle, right? So let's say the surface atoms has 50,000 surface atoms, and so you can compare the number of bulk atoms should be inside the nanoparticle, and that should be inside this guy. So let's take volume, right? Now volume of what? Volume of atoms, a volume of a sphere. So 4 by 3 pi. Now R should remove the surface atoms, right? So let's take R minus delta R. So delta R is for this surface thickness, which is very less, right? Which is very less because it is only one layer of atoms, right? So let's remove that one layer of atom, and you can easily write r minus delta r equals to r for larger radius, right? You cannot write for nanoparticle because r itself is very small, so delta r also will be very small, right? It will be also small, so they are both comparable. Now, so the number of atoms should be 10 cube times this 50,000. So that will be not even 10 cube because 10 cube is already here, so it should be more than like 10 cube times cube. So let's say 10 to the power of 9 into 50,000. It's just for example, okay? You can calculate it yourself. You can try taking a big particle and then assume it is made up of this many of atoms, and then you can just try to equate this number of atoms to the volume. Okay? Now, let's draw. So these 50 surface atoms have lost one atomic bond. So let's say, okay, let's define a term. Let's say the bond breaking energy, right? So let's take it as epsilon. The energy required to break one bond, okay? So that should be equal to, for nanoparticle, the total energy of the system, the total energy of the nanoparticle will be equals to 50 times, so yeah, this is the excess energy that you need to provide for that to happen, and plus this 120, the surface atoms. So this guy's energy remains same, right? There is no difference because the atoms are there inside the bulk. There was no disturbance, right, for them. Now the same goes for this guy, bulk one. So bulk will have 50,000 plus the 10 power of 9 times the 50,000. Now, if I try to plot this energy, so let's say the energy of the system will be equal to, so 120 times the surface atom. So surface atoms mean, sorry, this is a bulk atom, right? So erase this part. This is about bulk atom. These are bulk atoms. Same for this way, bulk atoms. And bulk atoms have like satisfied all the bonds, so they are at minimum energy. Let's take minimum energy as E2 and the higher energy as E1. The atoms which are at surface, right? They have excess energy. E2 and E1. And for this is for nanoparticle. Because 120 atoms are here, so 120 times E1. And here we have 50 atoms which are at higher energy state because of one bond being broken. Right, they are at, so E1, this is E2. Okay. Now 50 E1 plus 120 E2. This is the total energy of nanoparticle. Now you can see this value will lie somewhere between here, right? So for example, if this is my average, if I have 50 here, then the line should lie here. But instead of 50, let's say this has 100. So for just clarity purposes, so this is my 1/4. This is my half. This is my 3/4. Right. So it should lie here. Right. This is my E total energy. Now you can say, okay, this is for, so here you can say, from this you can say that E1 is, so E1 is greater than E total is significantly greater, right? It is 1/4 part above. So E total is greater than E2. Please remember this relation. What does that mean? So E2 means every atom is totally bonded with all other atoms. It's completely satisfied in octane electronic configuration. That is perfectly coordinated. So everything is at minimum energy state. Right? Everything is bonded, everything is good, everything is at minimum energy. Now, E total means there is something discrepancy there. That means some broken bonds have been broken, and because of that, we are at higher energy state when compared to E2. E2 is nothing but equilibrium state. Let's add, let's write for E total for 1 micron particle. There you have seen this is for E1, same. E1 and E2 are same. There was only one bond being broken. E1 is for 50,000 atoms, 50,000 of E1. And what about E2? E2 is 10 to the power of 9 times 50,000 of E2. Now tell me, what is the addition of these two? What is the total energy? Total energy of 1 micron particle. 50,000 times E1 plus 10 to the power of 9 times 50,000 of E2. Now let's take out E2, 50,000 as common. E1 plus 10 to the power of 9 times E2. So what is this value? What is this guy's value? So you can clearly state that okay, because my 10 to the power of 9 number is very much greater than 1, right? So my 10 to the power of 9 is very much greater than 1. Then that means E2, 10 to the power of 9 E2 plus E1 will be approximately equals to 10 to the power of 9 E2. Right, so my total energy is 50,000 times 10 to the power of 9 times E2. So what is this? E total will be equals to, for 1 micron particle, what is this number? This number is nothing but E2, right? Yeah, this number is nothing but E2. So my total energy of 1 micron particle is E2. That means I am at equilibrium. So my line actually lies little bit above here. So it should be like this. Not very much above. So my gap is so small, I can just relate it to E2. That means my particle is at equilibrium, right? But what about the nanoparticle? So let me write this relation. So E1 is greater than E total of 1 micron particle, which is approximately equals to E2. But this is not the case for E1, sorry, the nanoparticle, because it was lying somewhere considerably above here, right? So from this, we can directly tell, yeah, whenever we are talking about nanoparticle, because the bulk atoms are very low in number, when you add the surface atoms and bulk atoms energy, it will considerably lie above. But for the large particles, which is not the case, because we have so many number of bulk atoms inside our material, that number will dwarf our surface energy number. So that's why we say, okay, when you have a steel block, yeah, steel block will remain same. If you put it in a container and seal it, and you say, yeah, my steel block will remain same even after 10,000 years or 20,000 years. Why? Because there was no atmosphere, so it will not rust. First of all, let's say there is no rusting, and you see that, yeah, steel block remains same, but not the case for nanoparticle. When you put two nanoparticles close together, they will fuse together because the surface energy is so high. They will just, so not the surface energy, their total energy is so high, they will do something and they will infuse together and they will become bigger particle. So this is the relation. You can understand why we indirectly say, even though it is indirectly, we normally say that yeah, nanoparticles have high energy when compared to bulk particles. So this is the reason. So not this is the reason for this thing, the energy difference between nanoparticle and bulk particle. So I hope I cleared it, because many people, even though they just say yeah, nanoparticles have high energy, but they do not know how that relation came from. Right? I have seen many people who doesn't know why do you say that nanoparticles are high energy. So this is the mathematical way of treating, simply treating. It's not like more involved in quantum mechanics, right? Just a basic statistical thing. Just do the addition and do what is the total energy of the system. Yeah. So that's how you see here. Whenever the particle will shrink, the number of atoms on the surface will more and more will come out. No, it's not about the more and more atoms will come out. No, the ratio between the surface atom and bulk atoms will become more and more like equal, right? So here you can see the fraction and surface atoms are more or less 1:1 ratio. When we are talking about the big particles like micron particles, then the surface to bulk atomic ratio is very small, right? So let's say so ratio will be number of surface atoms divided by number of bulk atoms. So this ratio will be very small for large particles, because the bulk atoms are so many that this ratio will be tending to be 0. But for nanoparticles, which is not the case, the ratio will be more or less a good value, which will be nearing to 1, right? So that's what you see here. See? So it's like less than 100 nanometers. You enter this regime, right, where you will see my particles ratio is not that much different when compared to surface to bulk. So there are different relations. I hope sir has derived one relation, right, where there was taken as a density and also those things. So I will not discuss those things because those are easy derivations and sir also has derived those things. So let's move on to the surface properties. Now how do I define my surface energy? Right. So sir also has described the two terms. One is the surface tension and another is surface energy. These two are more or less related to like the surface characteristics of any material. You take liquid or solid, but surface tension is more towards, when we talk about the liquids, we talk about the surface tension, and when we talk about the solids, we talk about the surface energy. Now why we do have two terms? Why we should have like one term for both these surface characteristics of liquid and solid? So that comes from here. Let's say this is my, let's say these are my rods, steel rods, okay, and I made a bubble here, a surface film from soap, okay. Now there is another rod, so these are like stiff, these are rigid, they will not move, but this guy will move, can move, right, it can slide. So I have made a bubble, not bubble, soap film. Now what I am trying to do is, now I am trying to pull this thing, right, with a force F. Let's say it is a force F. Now this liquid film will stretch, right? So this liquid film will stretch. Now the total energy of the system, again, total energy of the system will be energy coming from bulk plus the surface energy. Okay, now this is before pulling. Now what happens after pulling? Right? After we pull, there will be change in free energy. Now how do you write that? The dg, right? The change. Now the change in bulk energy plus the change in surface energy. Now again, this is surface energy. Please remember this notation because many of us get confused. Surface energy per unit area times the area will give you total surface energy. Okay. Now, because the bulk energy will not change, right? The bulk energy remains constant. There is only the stretching there, so the bulk atoms will not break. There is no breaking of bonds. There is nothing happening there. So this will turn out to be 0. Now dg will be equals to, this is my surface energy. So let's do the differentiation by parts. First let's differentiate area. So surface energy will remain constant times change in area, plus now doing for the surface energy, the area remains constant, the change in surface energy. Now how this energy, the change in energy, will change with respect to the change in area. So this change in energy of the system with respect to change in energy of the system with respect to, and because I have increased, because I have pulled, the length is changing from L1 to L2, and this breadth will remain constant. And because the length is being changed, so my final area will be L2 times B2 minus L1 times B. That means there is a change in area, right? And if I take that is a small area, very small, it will be dA. So the change in energy of the system with respect to the change in area of the system, right, will be equals to, all I have to do is just derive with dA. That's all. So at first I will have surface energy plus A, because it's constant here, so D. This is very important relation when you are dealing with the surface, any surface characteristics of any type of materials. Right? This is a very important relation. Now, here comes the funny part. Okay. When we are talking about the liquids, so first case is liquids. Now, when you try to cut a liquid surface, so many of us have tried. In childhood we try to do cut the liquid surface. So whenever we try to like put something into the liquid and we take it out, so the liquid will again come to the place, right? So first I have undisturbed medium. Now I try to insert or cut the surface of the medium, cut the surface of a liquid. So after some time, when we try to cut, the liquid will flow outwards. And after that, again the liquid will come back, right? And finally you will see no change. So what's happening here is, whenever you try to shear or cut the surface of a liquid, the liquid will make it so that it will come back to its original positions. The liquid atoms will can take that shear, right? So that is what happening here. That means the energy of the atoms is remaining constant before and after, right? The surface energy is remaining constant before and after, it is not changing, right? Because the atoms are rearranging themselves. Whenever you try to disturb the water surface, after some time the atoms will try to rearrange themselves and it will become the same again as it was before. So in liquids, it's nothing but the liquid atoms have that capacity where they can rearrange them, so that means they can easily move. So there is a motion in liquids. So that is what happens. Now, in liquids, the surface energy term will remain constant. The surface energy term will remain constant. Why? Because the liquid atoms have this degrees of freedom to move, but not in solid atoms. In, for example, if you see the atoms in any solid atoms, they will not move, but in liquid they can easily rearrange themselves. So that's why this surface energy term remains constant. When you do the differentiation, it will become 0, right? There is no change in surface energy term. So that's why if it remains constant, then differentiating with respect to area will be 0, right? So that's why for first liquids case, dg by dA will be equals to gamma. That's all. So that's why the surface energy and surface tension are both same. They both give same values in liquids, right? So that's why we just take surface tension term. There will be no surface energy term because they both are same in liquids. Now moving on to solids. The second case is for solids. So G by dou A will be equals to gamma area right. So yeah. Now in solid, so when I try to cut any solid, so for example, if I have a wooden box and if I try to cut it with some knife or like any wood saw or anything, the surface will remain cut. Right? There is a change in surface energy because the atoms cannot rearrange themselves and just stay as before, just like in water. Right? You cannot cut the surface of the water because the atoms first they will move, but again they will come back to the same position because they are continuously rearranging themselves so to distribute that energy. Right? But the same case is not in solids. So that's why there is change in surface energy. That's why this term will not be 0 anymore. And then the change will be gamma plus A. And because there are a lot of terms involved here, we just simply say it surface energy. That's why we use two different terms for liquids and solids. Why? Because of the rearrangement, the atomic motions. Right, for liquids the surface energy will not change, but solids it will change depending upon either you do the deformation or any other thing. Right, now moving on to this part. Yeah. So sir has discussed few things. Now before coming to this part, let's add one more slide. Yeah. So this is about the energy of the system. Now how do we quantify that surface energy term? So how do we quantify this term? Right. So far we have discussed. So yeah, nanoparticles of high surface energy. These things have high surface energy. Some other particles have high surface energy. So we have discussed different things like why do you have high surface energy. Now that is the qualitative part. Now we know that yeah, surface energy is there or surface energy is not there. That's all. We do not know what is the amount or what is the exact quantity. Right? Now how do we quantify? So simple. Again, if we do go with the classical model, we just consider the number of bonds being broken. Right? So larger the bonds are being, the higher the number of bonds are being broken, the more will be the surface energy. Less the bonds are broken, less will be the surface energy. So that is the classical way of relating two things. Right? Now let's take, so for example, so let's take the structure first. Let's talk about let's first before that also let's discuss about different types of crystal structures. Right? So let me add one more slide for that. crystal structure part. Crystal structure. I hope everyone knows, but still I will do a small repetition here. Okay. Now, let's say this is my simple cubic. So in simple cubic, I have 8 atoms. Now let's only talk about simple cubic here, because there are a lot of crystal structures, there are complex crystal structures. We will come to that. But for understanding purposes, let's take simple cubic structure, because if I try to involve HCP, which is hexagonal cubic closed pack structure, it is, even though we can do it, but when we are trying to understand a thing a first time, it will be very much helpful if we keep things as simple as possible. So let's try to do everything with simple cubic for now. You can even try for FCC at last. Okay. So here again, so each atom is bonded to 4 other atoms, not 4, 9, it's not 4, so it's 1, 2, 3. So there is other atom also here, because there is other cube also here, right? So other simple cubic here, and there is other simple cubic in the front. There are 2 cubes in the front. So from top view, if you see from here, it will look like this. So this is my carbon atom, any atom. Let's not take carbon atom. Let's take, it is a atom A. So this is my A atom. From top view, it will look like this. Right? If I am trying to look here, it is bonded to 4 other atoms. Now, one atom is below and one atom is above. So how many? So coordination number is 6. So each atom should be surrounded by 6 atoms. Then that atom is at lower energy state in simple cubic. And I am talking about simple cubic. So this is how it is. Each atom should be near to, let me draw that so that people can understand more. So I am only talking about this plane. Okay, it is plane 1. So here, if this is my atom, so this is the other atom, it should bond it to forward atom, and this is the back atom. Right, so everyone is same here, there is no difference. Okay, so there is no difference at all. Just give me a minute, I guess meeting has stopped. No, let's continue. Yeah, let's continue. So if I am talking about plane 1, so this is about plane, this plane, the top plane, and we are talking about this atom, which is this guy. We are talking about this atom. Okay, now it is bonded to 4 atoms on that plane. Okay, now what about, there is below atom, right? So there is an atom below, and the same goes for the atom above. So you can see this one guy is surrounded by 6 atoms, right? You can even see the distance between them. So because it is a cube, so cube has all equal sides, then the top will be A, the side one also will be A, this one also will be A. So bond length is same. Then this one atom is surrounded by 6 atoms, and that means that atom is at lower energy state. So everything is being satisfied. So that's why we call it as coordination number. That means each atom is coordinated by 6 atoms. Right. So this will be helpful when we deal with the surface energy part or problems in the next week or so, because I guess this week will be the last for the surface energy. So sir might have missed giving you problems in assignments. So he might give you next week. So I'm just telling you because you shouldn't feel surprised whenever you like do the assignment problems. You should know at least, yeah, I have read or seen this before. So for simple cubic you have coordination number 6. So each atom is like coordinated by 6 atoms. Cool? Okay. Now, yeah. So my energy will be, if all atoms are there, so my total energy will be number of bonds, or let's write it as this. Now let's not talk about number of bonds. Let's talk about coordination number. So that will be much more explainable, right? So instead of talking bonds, let's talk about coordination bonds. Coordination number. So the total energy of this atom will be coordination number times the bond energy of the bond energy of one, the bond energy between two atoms, right? So that will be equals to delta H, or enthalpy of bond break or bond formation. So this is the enthalpy of bond breaking or bond formation times divided by 2, because I am talking about one atom. So bond is actually formed between two atoms. So whenever you have a bond, it will be formed between two atoms, right? So that's why I am talking as delta H by 2, because I am talking about only one atom here, atom number 1. So that's why delta H by 2. Let's say this is the total energy of this atom, right? Now whatever the excess energy or the surface energy, whatever the excess energy. See, whenever you have said before, the G total of the system will be equals to G bulk plus G surface. So G total minus G bulk can be written as G excess, right? So the bulk should be the ideal energy the atom should contain, right? If you are at equilibrium state, then that is the ideal state. So that we can even call it as ideal energy. Now, if I am trying to remove the bulk part and still I find some energy, which is the surface energy, we call it as an excess energy. So we can write that excess energy as number of bonds being broken, right? The number of bonds being broken times delta H upon 2. Right? So this is our excess part. Now let's break some bonds. Okay? So if this is my simple cubic, now what I am trying to do is I am trying to cut. So I am trying to cut how? Let's say this is my cutting plane. So I am trying to cut this thing in half. Okay, so then it will look like this. This guy. So it will more or less look like this. Right, and because it is being broken, so that will look like this. Now what's happening? So this guy, now let's talk about the below part. It is same with if I'm talking about below part or above part, because I'm just cutting in half, the above part and below part will be same. It's just a symmetry, mirror symmetry, right? The above and below are same. There is no difference. Let's talk about the below part for now. So this guy has lost one atom, one coordination number. one bond. Below he is good, and on left and right and forward again he is good. So the number of bonds that has been broken will be how much? Yeah. So that will be equals to number of bonds been broken times what is the total energy? It will be coordination number into delta H by 2. Now why I include the Z also here? Because this term will tell me how do you say that? Oh, sorry. The Z times delta H by 2 will tell me what is my enthalpy, right? The enthalpy of breaking per mole. So that's why I'm including Z also here. So that's how I can take surface energy will be equals to N times Z into delta H by 2. Or you can just remove that Z and you can just tell me that delta H is for only breaking of energy for one bond. Then you can just take out this term. There is no need for this coordination number here. Okay. I hope I am clear. So again, if I will explain even in simple terms. So for example, if I have 1 mole of copper atoms, okay. So to break every atom in the 1 mole of copper atoms, so what I try to do, I need to supply some energy, some heat energy, right? So how many bonds do I need to break? Coordination number, right? The coordination number times the delta H of each bond divided by 2 into Avogadro number. And because I'm talking about 1, so 1 times Avogadro number. Right. Now I do not know, if, for example, if I don't know what is my delta H of breaking for one bond, so it is not easy to calculate, right? For single bond, how can you, we cannot like just take two copper atoms and break them. So it is not possible, right? So for that, what we do is, we simply take for one bond, this is for one bond, right? This is for 1 mole. Okay, so this is for 1 bond. Now I just shift everything there. So it will be 2 times delta H per mole. This is easy because 1 mole of copper atoms is easy to do, right? Because it is just the delta H of melting, right? That's what we are trying to do. Delta H of melting is nothing but we are trying to loosen that bond from solid to liquid. Right, the liquid atoms can easily move, but not the solid atoms. So we are trying to break the bonds of solid atoms when we are trying to heat from solid to liquid. So that's why this will be delta H of what, melting, and this is standard value. We can get it anywhere. Times divided by coordination number into NA. So again, I guess I made a mistake here, so it's not Z here, right? So you can just dump this term here, right? Because the delta H, 1 bond, you can just put this term here. Then what happens? It will be equals to Avogadro number. Oh, sorry, this is the number of atoms, broken bonds. Number of broken bonds, not Avogadro number. 2 times N into delta H of melting divided by coordination times into Avogadro. So this is very easy relation. This is a more or less simple classical relation. Okay, to know the what do you call the surface energy. Now I am trying to cut my simple cubic. If here you can see, I am trying to cut my simple cubic into half. So this is my bottom half. Now because here my N, what is the value of N? The number of broken bonds. The number of broken bonds here is 1. Why? Because I will draw this again here so that you people can see. clearly. It is hard to draw with the lines like this, right? So this is the bottom half. Now let's take it. Yeah. So this line, this plane has been broken. So my simple cubic, which is this guy, is cut in half. So this is my bottom half. Now the same, if I take even a above atom or below atom, it will not change much, right? Let's talk about this guy, blue atom. This guy, okay, this is the blue atom, which is the main hero or focus here. Let's take a look. So this atom is good. There is no disturbance here because we only cut above. We have only cut the thing above. So the same goes for this guy also. He is also not disturbed, right? And there is a cubic. There is also another cube left side also. So there is another cube here. So it is only cut from above. So there is no disturbance in the below atoms. The same goes for this guy, and there is a cube also forward. So I hope you people are understanding, because see, I have explained what is the difference between particle, grain, and crystallite. So crystallite is a part of a grain. So what do you know crystallite? Crystallite is a collection, three-dimensional collection of lattices. So it's just lattice point. That means the lattice structure, the crystal structures are arranged like this, one by one in 3 dimensions. So we are only focusing on this one guy, right? So it is surrounded by all the other same lattices, right? Now there is also lattice below. So there is also an atom below. Let's take green. So I have a below atom. Now what about the above one? So above one bond is being broken, right? That's what we are seeing here. So now what is the number of bonds being broken? Here you can see the coordination number is 6. But what about here? It is 5. That means one bond is being broken. Now whenever I am telling about cubic or simple cubic, and if I try to cut the surface in half or cut the cube in half, then my number of bonds being broken will be 1, right? Then what will be this formula? So it will relate turn up. So I will write it as BB, or bonds being broken. Okay. There is another B, right? So let's write it as BQ. Oh, I can write it as BBB, right? That will be too much. So I'll just write it as BQ. That means, okay, again, it will be too much to comprehend. BQ will be too much to write. So let's simply write it as bonds being broken, okay? Yeah. Now the surface energy will be equals to 2 times my n is 1, the number of bonds being broken, times the delta H of fusion or melting, divided by the coordination number, which is 6 for simple cubic, times my Avogadro. So what is my value here? 3. So delta H melting upon 3 times. So now we know how to physically quantify the surface energy, right? For a cube, just for a simple cubic crystal, simple cubic crystal structure. Okay, nothing else. We are not at the surface level. Okay, we are just only on the simple cubic level. Now, moving on to the surface part. Now, till now we have defined for cube. So, for if you have a simple cubic crystal structure and you cut it in half, we know what is the surface energy. Now what if I am trying to do with a grain itself, right? A very big single grain. Okay. Now I'm trying to cut that big single grain into half, or let's not even perfectly half. Let's say I'm trying to cut at an angle. So let's say before this, my cube looks like, my grain looks like this. Just for understanding purposes, nothing else. Grain doesn't look like a box. Okay. So let's just say it looks like a box. So now I'm trying to cut this in this shape. Right? Now, if I try to zoom it and if I show you, this is how it looks like. Okay? Now, what is the number of atoms that are being broken? How do I calculate that? Now, after that, I have to calculate the surface energy. The surface energy is nothing but the number of atoms that has been broken times the bond energy of each bond. Right? Bond energy of one bond or each bond. Simple. So that's all. These two terms I need to define. So how do I arrive to this guy? So because I'm cutting in half, in not in a perfect sense, right? Then, so when you try to cut anything surface into half, it will not be perfectly smooth. It is jagged, right? So this is how it looks like. So there is a step formation here. It is not perfectly smooth, it is jagged, right? So when you see it more clearly, so there is this horizontal part and there is this vertical part. I'm talking about this one. Okay? This particular one. Let's remove this line. It's too much. Yeah. Now I'm trying to zoom this part, okay? So this is my horizontal part and this is my vertical part. Okay. Now horizontal part also has lost some bonds. The vertical part also has lost some bonds. Right. And there is also this third dimension. It's just not a simple side. It's in three dimension, right? So in horizontal, I have lost few bonds. In vertical also, I have lost few bonds. And third z-axis also I have lost few bonds. So now how do I calculate this? So for simplicity, let's remove this part here. For simplicity, let's just take a unit length. Let's take it is only 1 unit length. So this diagonal is only 1 centimeter or 1 mm or anything you want to take. Okay. So if this is 1, then what will be my this one, and what is my distance? This one. So let's draw a triangle. If this is my 1, then if this is my theta, this should be cos theta, and this one should be sin theta. Right. So what do you mean? How do I relate to that? Because cos theta will be equals to adjacent side by hypotenuse, and because my hypotenuse is 1, so adjacent side will be equals to cos theta. So that's how this length will be cos theta and this length will be sin theta. Right. Now number of bonds being broken in this cos theta length. Right. And because lattice parameter equals to A, that means 1 bond. Right. So the number of bonds, how do you know there are number of bonds? You just add this. It will be A. Right. So what is each bond length? Then that will be equals to cos theta by A. Number of bonds. Right. So each bond length is A, then the total distance will be number of bonds. I hope I am clear. I will explain it again. So each bond length is A. Then the length of all this uh, cos theta will be equals to this many number of bonds, right? So larger the bonds, the larger will be the length. So the number of bonds will be cos theta upon A. Now what about in horizontal direction? Now what about number of bonds being broken on vertical one? Again the same. Each this distance is A. Then the number of bonds being broken will be sine theta upon A. Now, so number of bonds being broken will be equals to cos theta upon A times 1 by A. Now why there is 1 by A? Because it is coming from Z direction. In Z direction also there is a breaking of bonds. So that will be equals to cos theta by A into 1 by A plus sin theta by A into 1 by A. So this will be equals to cos theta upon A square plus sin theta upon A square. That's it. This is the number of bonds being broken. Right. Now moving on to this formula. So total energy, the surface energy will be cos theta upon A square plus sin theta upon A square times delta H for one bond upon 2. Right? Now moving on to so this is how it looks like. Now what I'm trying to do is I will try to take 1 by root 2. Okay, so 2 will be equals to root 2 times whole square. I hope everyone knows. So this will be 1 by root 2 cos theta upon A square plus 1 by root 2 sin theta upon square times delta H for one bond divided by root 2. So how does this look like? So cos A cos B minus sin by sin B. So cos 45, right? So it will be cos of 45 minus theta. Okay. Positive. You can take any values, or you can just then you can see yourself what will be that value. Okay, there is one bond for one. So this is my E surface energy. Please remember this equation. Yeah. Now if I try to draw in not coordinate axis x and y, if I try to draw in the spherical axis like r, theta, phi, okay, then if this is my origin, so E versus theta will be looks like this, and if I just draw for this function, okay, so it will look like mistake here. They shouldn't look like this. they should reach minimum value here. Okay, so my E versus theta will look like this. Here, this relation, I will write it above. Just a one, I hope you will understand this. Just one line, okay? It's not two lines, just one line. Yeah. Now, E is a function of theta, so cos theta minus 45 minus theta, it's on you. What you want to, which sign function, which sign you want to take. So for one bond upon root 2. This is how it looks like. Okay. Now, so what does it imply? So good. We have moved from simple cubic structure to grain, and then we have cut a grain in half in some, not in a perfect manner, but in a diagonal manner. Then we try to calculate what is our total surface energy, or the number of bonds, the total surface energy, which depends upon the number of bonds and the bond energy per unit atom, bond energy per bond, right? Divided by 2, because in one single bond there is an involvement of 2 atoms. So for each atom, the bond energy will be half. Okay. Now, to continue with this, we had to calculate the n value. So n value is the number of bonds being broken. For that, we came to we resolved this unit length into cos theta and sin theta. Then if each lattice parameter, like each bond length is a, then the total bond lengths, I mean when you combine all the bond lengths, is cos theta, and each bond length is a, then the number of bonds will be cos theta by a. And the same goes for z axis also, which is 1 by a. And when you combined those two, yeah, so this is how cos theta by a into 1 by a is cos theta by a square. Same goes for vertical one, so this one sin theta by a square in times each bond energy. So again, we just did some mathematical jugglery. So 2 is written as root 2 times whole square. Then so 1 by root 2 cos theta by a square plus 1 by root 2 sin theta by a square. So that will be cos of 45 minus theta times this. Now if I try to draw a graph, so this is how it looks like. Now what does this imply? That is the main question. So as I have said before, the system tries to, if it wants to stay in an equilibrium state, then the system will try to attain a minimum energy. So here you can see, where do you get our minimum energy? So you get a minimum energy at the cusp, right? So this is called as cusp because the curves are converging here. So this is, let me draw with another color. So this is one cusp, this is another cusp, this is another cusp, and this is another cusp. Okay. Now, if I draw a tangent here, see, with at this point, this is my tangent, and our same goes here. This is my tangent. This is for this point. This is a tangent. Right. So, and these curves are at minimum energy. Right. And whenever you draw a tangent at that point, they will cut the surface like this. And this collection of points or this collection of tangents will tell you the equilibrium shape of any object. So this is also called as Wolf net. Okay. From Wolf net, you can easily define what should be the equilibrium shape if I draw my relation between, if I try to draw my relation between energy versus the theta, right, how I have cut the surface, that will tell me what is my equilibrium shape. So what does it tell me? It tells me my equilibrium shape is a cube, right? So what we are trying to do from like last half an hour, we are trying to like, where was that? Yeah. So from for last half an hour, we are trying to do everything with last half an hour or more than half an hour. We are trying to deal with what is the energy, what is the surface energy if we try to cut a cube in any direction. Right. So we finally arrive to the same point, that our equilibrium should be cube. That's it. So that's how you arrive to the energy of that. So if we take FCC, this relation will change, right? Because each atomic planes. So for FCC, let me draw. So so let's say these are my atoms, right? The corner atoms. Okay, and then I have the face center atoms. Okay, so not only at the corners, I have atoms at face centers also. Right. So again, this is one thing. So if I try to cut the surface here, so if I try to cut here, that will be different, because this atom, for example, if I take this atom is not shared by these guys, blue guys, but these are very near to the red one. So in FCC, you will have coordination number 12. For BCC, you have coordination number 8. Now because the coordination number has changed, that means if I try to cut the surface in the horizontal one, it will not be 1, right? Because I have lost 1, 2, 3, 4, 5. I have lost 5 bonds. So if I try to cut in 1, 0, 0 direction, again I hope you people are good with this notations in metallurgy. So 1, 0, 0, nothing but draw this again. So if this is my axis, and if this is my crystal, if this is my crystal, then this plane will be called as 1, 0, 0, and this plane will be called as 0, 1, 0, and this plane will be called as 0, 0, 1. And what about if I have a plane like this? I hope people can clearly see it, right? Yeah. What about this guy? Okay. Sorry. So what about this one? The red plane. So that plane is called as, so it is touching 1 and 1. So it will be, it's not touching 0, 1 y-axis, right? So that's why it will be called as 101. So it's just where it is intersecting, that's all. So depending upon that you will get a number here. Okay, so if it is intersecting at half, then that number will be reversed, that's all. So if this plane okay, now moving on to 111 plane. So 111 plane will look like this. So because it is touching all three axes, so it will look like this. Okay. So my green one is 111. Why? Why? Because it is touching all three coordinate axes. Right. So it is touching this one, this one, and this one, 111. Now, if this intercepts at half, for example, if it intercepts here, then so everything will be 1. Everything will be, so each will be taken as a 2. So it will look like 2, 1. Okay, no, not 2, 1. Yeah, it will look like it is intercepting at 1, 2. Right. So if I want to know the coordinates, it will be 1. If you use a reversal, then it will be 1/2. It will be 1. That's all. Now it depends on which direction I'm trying to cut. Right, if I'm trying to cut in the horizontal direction, or this cut will be what, 0, 1, 0. So if I'm trying to cut in 0, 1, 0 plane direction, right, then the coordination number will be 5. What about if I'm trying to cut like this in 111 plane direction? So if I'm trying to cut the cube like from top view, it will look like this. I'm trying to cut like this. No, it's not like this, but if I see it from side, yeah, it should see from side. So side it will look like this. So this is my what? This is my origin. This is my 0, 1, 0, and this will be my this point, right? It will be my this point. Yeah. Oh, sorry. It will be this point if I'm trying to see from this side, right? So it will be 0, 0, 1. I guess I'm wrong. Yeah. So above this point you will get 0, 1, 0, or 0, 0, 1. Sorry. So it is more complex. I hope you can like visualize it. So I am trying to cut along 111 plane direction. So it's just a sliding of crystal structure along 111 plane. Okay. So initial cuts were simple. It's just along what, half. Where is this guy? Yeah. It is just along half. It is along 0, 0, 1. Right. 0, 0, 1 or 0, 1, 0. It depends on what you are taking, x and y and z. Right. So if I'm trying to cut along 111 axis, then my coordination, the number of bonds being broken will be 3. Right. So if I'm talking about 1, 0, 0, then it will number of bonds being broken. Number of bonds being broken. So you can see from here. So if I try to cut it here, this is bonded to this guy. This will be out, and this guy will be out. So yeah, all atoms on above. So it is 1, 2, 3, 4. So 4 atoms will be lost. 4 atomic bonds will be lost. But for 111, 3 will be lost. It's only a visualization because I cannot draw a 3-dimensional diagram in 2D here. I have to find good images for that. So in next session I will try to find the images, and I will try to even share links for that. So that will not be a problem because I cannot draw those things here. So It's just a visualization game. People can do it. It's not very big. All you have to do is just take some tea, sit quietly somewhere, and then just visualize. Okay, this is the atoms. So these are the atoms. This is the distribution of atoms. Then if I try to cut it from here in one plane, then these atoms will go away. So it's just a visualization game, right? So from here you know that if I'm talking about what is the surface energy of any crystal, all you have to do is find the number of broken bonds, the bonds being broken, BBB or whatever, n times, what was that formula, into 2, which is coming from there, into the delta H melting of that system, whether it is copper, aluminum, whatever it is, divided by Avogadro number into coordination number of atoms in that crystal structure, right? So this is my formula. Okay then. Now moving on to, now we have seen surface energy. Now let's move on to the particles, the nanoparticles. Okay, so again, nanoparticles have high surface energy, right? So we have seen it, we have even derived it. So when I try to put these two nanoparticles together, because of the high surface energy, so what I'm trying to do, I'm trying to put this together, right? Now what happens after some time, even at low temperature, I'm talking about room temperature, not high temperature. Okay, you know, when you try to put two steel blocks together at room temperature, nothing will happen. Now if you do that same thing at high temperature, they will weld, right? Because at high temperature the atoms can easily move, so there will be a welding if you apply some pressure, right? I'm talking about very high temperature, very close, not close to melting point, but yeah, like if I'm talking about eutectic steel, so maybe at 1500 degree or 1490 degree centigrade at a temperature. So at room temperature, our basic sense or basic knowledge should say these nanoparticles, nothing should happen to them, but because of high energy, as I had explained before, they will sinter or they will bond. So after some time, after time t1, it is at time t equal to 0, after time t1, it will look like this. So how it is happening, right? That means the first point, atoms are moving. Right, so for atoms to move, you need vacancies. I hope this is a very basic subject. For if you want some atoms to move, you need to have some vacancies, right? Then only atoms can move, or they won't. So I hope this is clear to you, because it's in itself again like 15 to 20 minutes thing. So I will not explain this here. If you have any doubts, you can ask later. But it's simple. So for example, okay, I will explain anyway in very simpler manner, but not in deep level. So for example, if you want to move in a room, the room should be empty, right? If there are, if a room can accommodate 20 people, and if there are 19 people, okay, then one person can easily move, right? As gap moves, right? Wherever the gap is there, the person like besides that gap can move, right? So that gap is called as vacancy, and the person is called atom. So for atom to move, the vacancy, it's indirectly the vacancy motion, that's all. So that's why we do not talk more about atoms, we talk about vacancies, because it is easy to visualize. So whenever vacancies move, that means atoms are moving, right? So that's how, that is the relation. Okay. Now let's move to the main topic. Yeah, so the first point is the vacancy, atoms are moving. That means there is a vacancy motion, or the vacancies, so somewhere, so there is vacancy movement. Okay, now how vacancies can move, right? There needs to be some energy, right? So how is this coming from? This is coming from flux. Now flux, how do you define that? It diffusivity times the concentration gradient of vacancies, dc upon dx. So we can tell as v, because of vacancies, mole fraction, right? For example, it's just how the water flows from high position to low position, from high energy to low energy, the same, right? So if there are 1000 vacancies and there are 50 vacancies here, then vacancies will move from here to here. That's it. So that they maintain like 1050, then they can maintain more or less 550. What do we call it? 1050, right? So 1050 will be to 5 to 2 to 525, 525, right? Yeah. The vacancies will move from high concentration to low concentration until they maintain vacancies same at every layer, right? Because at first you have 1000, here 50, so the vacancies move from higher concentration to lower concentration to maintain equilibrium, balance. Now that is the theory, right? Now how do we quantify? We know the atoms are moving, so because of vacancies motion, and this is the theory behind it. Now how do we quantify, right? Now again, so there is this formula that sir didn't derive. So the excess pressure will be equals to 2 times surface tension upon R, right? This is the formula. So how do we get that? I'll just derive it right here. So let's take, this is my surface film, okay, or bubble film, or you can take soap film also, anything, water film or water drop, surface film, anything. So, and because it is spherical, let's take a spherical drop, which is easy to visualize, and also people have seen, right, during raining, a teardrop, anything. Now because the atoms are stretching, right, because above there is no bond being taken, so because of bond broken, so these atoms will push inside, right? So that's why there is this tension here, because of the other part, right? There's a tension between these two. Now let's take it as a theta. Let's draw it nicely so that you can understand. Okay. Tension. Okay. Now moving on. Now let's resolve this part. Now if this is theta, then this will be theta, right? And this will be t cos theta, and this guy will be t sin theta, and the same goes for here also. Okay, so the horizontal, let's balance the horizontal forces, and there is pressure. This is the atmospheric pressure acting from outside to inwards, and there is this pressure from the liquid drop, P1, from outside to atmosphere. So these pressures are acting on, it has an area A. Okay, so far so good. So now balancing horizontal forces, okay, that will be equals to t cos theta equals to t cos theta. It is balanced out. Okay, now what about vertical forces? It is just a free body diagram, there is nothing new in it. Okay, so you add t sin theta downwards, it will be 2t sin theta equals to, what is my force? force equals to change in pressure, the difference in pressure, not change in pressure, difference in P atmosphere. P1 is greater, right? Because if P atmosphere is greater, then it will be concave instead of convex. Just simple basic understanding. The higher the pressure, the more will be the curvature in outside. If the curvature is more from this side, then it will look like this instead of this, right? Now 2t sin theta will be equals to excess pressure, or P1 minus P atmosphere, times the area. Now 2t sin theta equals to change in pressure times area. Now if we are considering very small area, so this theta will be approximately taken as sin theta, right? So sin theta will be equals to theta. So 2t theta delta p times a. Now what is theta? Theta will be equals to arc length upon radius. What is my arc length? Let's say it is dl upon radius is nothing but r times delta p into a. If I push this a that side, then it will be times area. Now this whole term can be written as surface energy, and because we are not dealing with liquids, right? See, even though I'm trying to represent it in terms of surface bubble as surface tension, because during melting, right, near the melting temperature, the solid will behave as a liquid. So that's why instead of writing surface energy, we just write surface tension during melting temperatures. Okay. So this whole term will be surface energy times, and this will be my R. So this is how we arrive to this definition or this formula. I hope I am clear now. You people might have misunderstood or couldn't understand this formula. So this is how it is derived. It's a simple free body diagram. Okay, there is nothing complex in it. Now, that is one part. So what is my, coming here, the atoms are moving, so vacancies, the atoms are moving but vacancies are movement. So at first I have energy G1, same two same type of particles, so G1 and G1. Before it is 2G1, the total energy. Now it is G2. So there is change in energy. So that how do you quantify? So again, that delta G will be equals to delta G naught plus delta PB. Okay. So if I am talking about per atom, then this volume is divided by volume of solid will be divided by molar volume. If I am talking about per atom, then this will be equals to 2 omega surface energy times R. So this will be my atomic volume. If I am talking about per atom, okay, atomic volume. Okay, now coming to the main part. So you people have seen again, the mole fraction of vacancies is equals to exponential. So if I have a solid copper block, so what is my mole fraction of vacancies at any given temperature? So what is the relation? So how do you find the number of vacancies inside this copper block at any given temperature? So that is given, the relation is given as this, exponential minus delta G upon KBT. Delta G is for formation of vacancy. Or the delta G is for system. Okay, delta G of a system. Total energy of a system. Right, now how do I arrive to this one? So XV is nothing but number of vacancies divided by total number of sites, atomic sites, or total number of sites. So total number of sites will be equals to number of atomic sites in a structure, in any system, number of atomic sites plus number of vacancies. That will tell me total number of sites. Now this is my number of vacancies. Okay, this is NT, total number of sites. And that will be equals to exponential minus delta G upon KBT. See, I can derive this. It's very simple relation. So what is the time now? It is, yeah, it is 4:55. We still have 15 minutes. So it will hardly take 5 to 6 minutes. Okay, then let's derive that part. Yeah. So now we know delta G will be equals to delta H minus T delta S for vacancies formation. Okay, delta H is nothing but the energy required to create vacancies for more, and delta S is entropy of vacancies. And we are not considering about the thermal entropy. Let's consider only configurational entropy. So configurational entropy, how do we get that? It's simple probability way. So what is the number of ways in which you can, so again remove everything, so starting from scratch. Let's say I have, these are my atomic sites. Okay, now I have, let's say, 6 atoms and 3 vacancies. The number of ways I can have a system with 3 vacancies, right? So the answer will be 9C3. What are the number of combinations of which I can have, I can have my system with 3 vacancies, right? It's 9C3. That's it. For example, if I have NT sites, again let's not use combination also, I will just write everything. Okay, first there are 9 sites, so it will be 9 factorial upon, vacancies are similar, so that's why there will be 3 factorial, and the atoms are also similar, so that's why you will have 6 factorial. It is nothing but 9C3 or 9C6, both are same. Okay, so if I have NT sites and n vacancies, then n factorial upon n atoms factorial times n vacancies factorial. Or you can write, instead of n atoms, because there are too many unknown terms, let's just write NT minus NV, which is again nothing but number of atoms. Now we know delta S equals to ln K. So this will be, it is not delta S, it is K. So it is ln K. Okay, then that will be ln NT factorial minus ln n minus NT minus NV factorial plus ln NV factorial. Let's not make it complicated. Let's take few basic assumptions. So we know NT is always greater than NV because number of sites are so large. Vacancies are very small when compared to atomic sites. So the total number of sites will be very large when compared to NV. And that means this will be 0. So ln NT factorial minus ln NT factorial, they will both cancel out. So the only thing that remains here is ln NV factorial. Now again, ln of any factorial is number of vacancies is not a small number. Yeah, it is a small number when compared to NT, but in itself it is not a small number. There can be 1,000, 10,000, 5,000, 6,000. So that is not, what is the 1,000 factorial or 6,000 factorial? That is not a small number, right? So that's why if our numbers are large, we use approximation called Stirling approximation. So NV ln nv minus nv. So this is the Stirling approximation. Okay, so this can be again write it as ln nv, right? So that's all. Then all you have to do is, so at equilibrium delta h equals to minus t delta s. So at equilibrium the delta h is equals to 0. So the delta s equals to delta h by t. And you substitute here. So that will be equals to xv will be equals to, all you have to do substitute here, then exponential minus delta h upon kBt. If I am talking about per mole or per atom, okay, I have got to know in terms of per atom. If I am talking of per mole, then it will be RT, universal gas constant times T. Okay, so yeah, we have arrived to this. Now there are two surfaces. If you want to see here, see, there is one thing called, yeah, come to it now. See, this is what, convex, and this is concave. This is how the powder particles look like, right? There is this necking region. There is this necking region, right? So there is a convex here and there is a concave here, right? Now what is the mole fraction of vacancies at both the positions? So that will be equals to xv will be equals to exponential minus delta g naught, which is about the bulk, plus bulk, okay, 2 delta gamma, so kBt plus 2 delta, okay, omega upon r kBt. So xv will be equals to this some constant, because it is a constant, right? So let's take k plus exponential 2 minus gamma r k b t. Okay, now we know if x is low, again exponential of minus x will be equals to 1 minus x. You can just expand this one, you know, 2 factorial minus x will be 3 factorial. But because the higher terms doesn't make sense, okay, these higher terms doesn't make sense, so what we just stick with only 2 values, right? So that's why xv will be equals to, yeah. And coming to this curvature part, so again sir hasn't explained this curvature part, right? So you people must have been confusing about, yeah, why do we take convex has less concentration of vacancies when compared to concave has high number of vacancies. So it depends upon curvature. So that means there is a negative term here, right? So for convex we are taking our curvature as negative, and for concave we are taking our curvature as positive. So again I will explain why we are taking those assumptions. For convex we are taking our curvature, right, k, that is equals to 1 by r as negative, and for concave k proportional to 1 by r equals to positive. Right, now how do you define any curvature? So in simple one dimensions, so let's take one dimensional line, right? Here is my concave and this is my convex. So let's say this is my curves, okay? So how do you define any convex or concave. We define it by double differentiation. Let's say this is y equals to f of x, or y1 equals to f of x, f1x, y2 equals to f of 2x. Okay, two different functions. Now, how do we define curvature? Curvature is defined by double differentiation. Now, how do you physically interpret double differentiation? Because we know double differentiation is nothing but you got a function, you differentiate, and then again you differentiate. But what exactly is that? How do you physically interpret? Right. I will show you how do you like physically interpret it. Okay. Now there is this function called average function. So what do you mean by average? So let's take what? Concave. For now, let's take concave. Let's take 3 points here, here, and here. Okay. Now, what is average? Average is nothing but sum of all the observations by total number of observations in probability, or in number theory. You just sum all the numbers and then you do how many times you did the summation. That's the average. Okay. Now let's see what is the average of these two values, 0.1, 0.2, 0.3 for concave. Okay. So that will be so that function is given as f. Okay. Average function minus f of 3. Okay. Or more or less I should write it as f of x at 3. Let's see this. Let's see this what exactly this means and how this is related to f double dash of x. Now what is this average function? Average function is nothing but f of x1 plus f of x2 by 2. It is simple. There is no nothing physics, more physics like it. Just a simple mathematics. So average of this function f of x will be equals to at point 1 and 2. At 1 and 2 will be equals to f of x1 plus f of x2 by 2. Now what is f of x1? It is just a distance delta x from here, and same delta x from here. Let's take symmetric, okay? Both are delta x from here. So my x1 will be x3 plus delta x. Sorry, x1, right? So x1 should be x1 minus delta x. x3 minus delta x plus, what is my x2? x3 plus delta x upon 2. So whenever you see this, you apply Taylor expansion. Okay. Now what is my Taylor expansion? x3 minus delta x will be equals to f of x3 minus, right, so f of x3 dash dx plus f double derivative x3 dx upon 2 factorial, and there is the other terms. Now let's do the same for this guy, x3 plus del x. What is that value? F of x3 plus f dash of x plus dx plus f double dash of x at x3 upon 2 factorial. Now when you add these things, and because see only the only the odd derivatives have -1, here it have positive, so odd derivatives will cancel out, then f average at x3 or x will be taken as, there is half, right, first half, so we will have f of x3, please remember f of x3 plus, I have 2 factorial, let's take only up to 2 factorial, okay, let's not consider the other factorial things, okay. So f double dash of x3 upon dx, and because I have 2 factorial, 2 will get cancelled out. So if I multiply with 2, so f of x3 plus half f double dash of x3 dx square, sorry, double derivative, right? Dx square. Now see, we are getting to a very simple correlation. Average, it's not mentioned x3, okay, let's just write it as x, so at 1 and 2, okay, 1 and 2, sorry, mistake here, okay, this is good. F of x3, let's just put these things, let's shift f of x3 to that side, so it will be minus f of x3, 2 will go there, so it becomes 2 times, there will be dx square f double dash at x3. Now we have reached to very simple correlation. You don't need to like remember, okay, convex will have what, concave, convex will have negative curvature, concave will have positive curvature. No, all you have to remember is this relation. See, so average, so what does this mean? Average at 1 and 2 near to x3 minus f of x3 divided by, see, just you need to remember this one, that's all. What is this value? Dx square is positive, it is differentiation, 2 is constant, it is a positive. So the only value that is determining our relation is this term. So average near to x3 minus f of x3, what is that value? Let's move on to concave. Okay, so this is my f of x3. So what is my average value near to this one? So let's take this value as 2, this value as 4, and because it is below, this should be 1. See, let's take this is 2 as, okay. Now 2 plus 2, 4, 4 upon 2 will be 2, 2 minus 1, which is a positive. So concave will always have positive curvature. Coming to convex, at first we need to find the average values. So let's take, this is 6, this is 7. So 6 plus 6 by 2 will be 6. 6 minus 7 will be minus 1, negative. So my convex will always have negative curvature. See, so that's how we arrive to this simple relation. You do not need to mug up anything. All you need to understand is how do you define our double dash of x, double derivative. Once you have that correlation, you substitute your values. Not only to this, you can do it for any curvature. Right? Even you can do it for, like, for example, my curve is like this. You can do it for this also. You don't need to mug up, okay, my slopes are changing or no, nothing. All you need to do is understand that how do I define my double derivative, and then substitute those values. You get the average. First you find the average values near to that point, minus that point. If it is positive, it is concave. If it is negative, it is convex. That's all. So that's how you come here, right? So that's why sir has taken for convex, this will become positive, and for concave, this will become negative. That's why the convex vacancies are less, concentration of convex are less when compared to concave. So this one curvature term will define this whole situation. That's why I have stressed out why do you need to understand this curvature function. So yeah, I guess it's above 5. I will stop this session today. If you have any doubts, you can ask, or you can leave, or you can just text in chat.